Additional information. Yes. Not a lecture. First announcement is, we are going to have another lecture on Thursday. That is on blasts.
Yes.
And can structures resist? So basically, it's all about blasts because these days everybody is talking about blasts. But those are gas explosions. But we thought we have an expert at Department of Civil Engineering University. So basically, there will be a lecture on Thursday. Engineer Manjula, what is the time? We are starting 6 o'clock. Engineer Manjula,
yes.
6 o'clock. 6 o'clock.
We started Thursday lecture also at
Thursday. Actually, it has been put as 5:15.
5:15.
So we are starting at 5:15.
Yeah,
and
it is like that.
Interesting lecture because I'll be touching on some of the aspects today. Yeah. So basically, there will be a lecture.
We are going to start
Dr.
now.
Dr. Lakshita Fernando will be doing a lecture on Thursday, 5:15 p.m. and that will be on blasts. Can structures resist? So basically, how to make the structures to resist blasts. And you talk about what is blast and how the waves propagate, and then what are the important parameters that we need to look into and so on. Now, today's lecture, I'm going to start working on the whiteboard because I want to show you a few important aspects. And although we call it medium rise, I'm going to start with the low rise, 5-story, and how to think about a 5-story building. Then I will extend it to a 10-story building, and then I will extend it to a 20-story building. So today we'll cover whatever we can, and the remaining part we will continue next week, Tuesday. What is the day, Manjula? Today is 22nd, 29th. Today is 21st. So 28th we'll have a lecture, is that right?
Yeah, we can have a lecture.
We can have a lecture 28th. So we are going to have another. So repeat of the the continuation of today's lecture will be on 28th. Because we are planning to have it every week so that you will get a good continuation. So I'm going to now shift the screen to whiteboard. So you have to excuse us for 1 or 2 minutes until we change from computer screen to whiteboard. So today, now we'll adjust the board as I write. We'll make some small adjustment so that we can see it. I'm going to take a small building, a common building. In this building, we'll have grid lines 1, 2. So we say 3, 4, 5. And this direction, can you see it? Distance will be 6 meters. All this will be 6 meters. And this is 7.5 meters. So we are going to have a grid this way, A, B, C, D, E, F. So let's assume that in this building, this elevation, I'll draw a small elevation, not the exact one, just to save the space for other things. We are going to have ground floor, first, second, third, fourth, roof. Roof is also a flat roof. So foundations will be like this. So the floor to floor height here will be 4 meters. All the other floors 3.6 meters. So first thing I'm going to show you is how to select the general, how to do the general arrangement for this building. As you can see, this is a simple building. It's a very simple building, and I'm going to show you how to do the general arrangement for this building. So let's see what are the special features. At the ground floor, you can see there's a 4 meter height, but we like to have the same height for all the floors. So how do you ensure that we maintain the same height? We can introduce the ground beam. We can introduce the ground beam. Now, this introducing ground beam is common for low rise, medium rise, all. So we'll introduce the ground beam. The moment you introduce the ground beam, what is the floor to floor height? 3.6 meters. So all the floors will have a floor to floor height of 3.6 meters. Manjula, can you hear me?
Yes, we can hear very well.
Very well, right? Right. So now, so basically now you can see that blue color, that's the elevation. That floor to height is now maintained at 3.6 meters. Now we have to see there are two options for this building. It's a 5-story building. 5-story building means we'll have a lift. So if you are going to have the lift here, I'm just drawing it in dotted line, 2 lifts. Now you can see the lifts are not symmetrical. If the lifts are not symmetrical, what is the way you can have the lift? Because you are going to have only 2 lifts. And we might have a staircase here. So when you are arranging, if you are going to have concrete walls, it will be costly. So one of the options available is to have corner columns. Only at the corners you will have some columns. And rest you can fill it with masonry. That means you are not going to have a concrete wall in this building. It's a 5-story building, no concrete walls. It's possible. If it is a 5-story building, no concrete walls. If it's a 5-story building, no concrete walls. What can you say? We say it's an unbraced building. Unbraced. Unbraced, which means lateral loads resisted by whom? The frame. Frame resists the lateral loads. Frame resists the lateral loads. So, if the frame is resisting the lateral loads, it's an unbraced frame. What is the difference between a braced frame and an unbraced frame? If you take a column in the braced frame, the column buckles like this. In the unbraced frame, the column buckles like this. There's a movement delta. With an unbraced frame, there's a movement at the top of the column. So the column will look like this. It will look like this. Whereas if it is braced, it will look like this. No significant movement at the top of the column. But if it is unbraced, we can have a significant movement at the top of the column. So you can see unbraced can buckle easily. It can buckle easily, whereas it is more stable. So what do you like? Braced or unbraced? We say we like braced. But if you are not going to have a lift core, we are having unbraced situation. So we have unbraced column. Now we want to select the column sizes, beam sizes, and the slab thickness. So if the slab is 7.5 meter by 6 meter, what is the thickness of the slab? It's a massive slab. The slab thickness will be about 175 to 200 millimeters. What can you say about the reinforcement requirement? Reinforcement requirement can be either T10 or T12 at 150 centimeters. T10 or T12 at 150 centimeters depending on the load. Slab thickness is 175. What can you say about the cost? Cost is high. So how do you reduce the cost? We'll have secondary beams. We'll have two beams like that. Now what happens? Now what happens is the E-line patterns will be like this. So all these rods will come here. All these rods will come here like this. Now you can see, now if you go for this option, what is the thickness of the slab? 125 millimeters. What is saving in the slab thickness? 50 millimeters. What is saving in the reinforcement? Now we need T10 at 250. We need T10 at 250 centimeters. Huge saving in reinforcement. So we prefer, when the spans are more than 5 meters, it's worth considering the option of dividing the slab by using secondary beams. Dividing the slabs by using secondary beams. Then I have to ask the question, how do you design the secondary beams? How do you design the secondary beams? We design secondary beams so that they are simply supported. So what is the difference between a simply supported beam and a continuous beam? Simply supported beam, what is the reinforcement that we provide at the top? 2T12. No need to provide any 16 millimeter bars or 20 millimeter bars. Why? It is simply supported. What is the reinforcement that you get at the bottom? 2T16, and then you get additional reinforcement to carry another 2T16 or 2T20 or whatever. You get additional reinforcement to carry the additional loads. Additional reinforcement. But the most important thing is, what is the bending moment used for design? WL squared over 8. Because secondary beams must be designed as simply supported. Secondary beams must be designed as simply supported. Is that clear? Modular?
Yes,
sir, yes, clear.
Yes. So you can see, we can make a significant saving by going with secondary beams, where the secondary beams are designed as simply supported. Whether it's Eurocode or British code, still the secondary beams are designed as simply supported. What is the reason for that? Now you can see, here we get a secondary beam. The secondary beam, supported by which beam? The H beam. The H beam. If you consider secondary beam is continuous, what will happen? This H beam will be subjected to torsion. It will twist. Why? You have a beam and that beam is bending like this. What will happen to this beam? This beam will rotate. What will happen if the beam rotates? It cracks. So we must make sure the reinforcement in the secondary beam is 2T12. 2T12. No, not enough fixity to rotate the H beam. But we have to be little concerned about this. There's some kind of fixity. So what is the preferred width for this H beam? 200 millimeter or 300 millimeter? What is the preferred width for this beam? 200 millimeter or 300 millimeter? We know the torsional capacity of a beam depends on the width, the minimum dimension. So if it depends on the minimum dimension, which is more preferable? The preferable width will be 300. It's not 200. Somewhere 200 you can manage, but don't use 200. Use 300. Why? There's a possibility of transferring a small moment at the second beam. Small moment, not a big moment. Very small moment. So if you use 300 millimeter width, then you are better off. You can resist torsion better. You can resist torsion better. Is that clear? I'm just trying to tell you how to select the member sizes with some logic behind it. Is that clear, Manju?
Yes, yes. It's clear.
Right? We are not blindly selecting. We are not looking at another structure and selecting. We have a reason for selecting every dimension. So now we have a secondary beam. Design as simply supported, 2T12 at the top, so that it will not cause any torsion on the primary beams. In the middle, here, no problem. Why? There will be another beam on the other side. We'll have another beam running here. So there's no chance for torsion. Whereas the H beam, though it's loaded less, still we select a reasonable thickness because it gives us a reasonable value for torsional resistance. Now we have a structure. We know the slab thickness. It can be either 175, 180 millimeters with no secondary beams, or you can go with a slab where you have 125 millimeter thickness, very much less steel and more economical, because beams are very efficient in carrying flexure. So we have deep beam, much less self-weight. So the secondary beam plus 125 millimeter thick slab can be much more economical than having a 200 millimeter or 175 millimeters. So that is the first lesson we can learn, which means we must do something to optimize the slabs. And if we can reduce the slab thickness even further, it's better. But when you are reducing the slab thickness a lot, you run into problems. So with that, we get an important question: whether we need grade 25 or 30, or 25 megapascal concrete, or 25 newtons per millimeter squared concrete, or 30. What is your preference? I mean, there's no need to go for 30. If you can manage with 25, no harm in managing with 25. But when you go for 30, especially when you are using the Eurocode, you can get some advantage with the cover. You can gain some advantage with the cover. So it's up to you. If I select grade 30, the reason is the cost difference between grade 25 concrete and 30 concrete. What is the cost difference? 500 rupees. 500 rupees. Grade 25 and grade 30 concrete, the cost difference can be 500 to 750 rupees. So, is it worth going for grade 30? Yes, you might say, yeah, it's worth. Think about grade 30. Why? You get a stronger building and a more durable building. You get a stronger building and a more durable building. Is it clear up to now?
Yes.
So, now we have beams. We have to select the beams. Now you can see we are talking about 6 meters and 7.5 meters. But there's a rule for all the buildings. What is the rule? Maximum depth. $600 millimeters. Any problem? Increase the width. You can't manage with a normal width of 250 or 300. Then will you increase the depth or width? We increase the width. Why? The reason is when you have a building, generally we need to have a floor to floor clearance of close to 3 meters. And then we need something like 0.3 meters minimum for 2.7 meters. You see, 0.3 meters minimum for the air conditioning ducts, and below that we get the beams and the slab. Overall thickness 0.6 meters. If you go beyond 0.6 meters, we'll have to increase the floor to floor height. We have to increase the floor to floor height. 5-story building, the penalty is not very much, but it's a tall building. The penalty can be about 2 to 3 floors. Extra facade, just because you have selected a beam of depth greater than 0.6 meters. Then you'll ask why this magic number 0.6 meters. The 0.6 meter deep beams are fairly robust. They are strong beams, So because of that reason, we select 0.6 meters. So if you look at this particular beam will have a concentrated load here and then very small loads here. Not very heavily loaded. So what is the thickness? What is the width you select? I might select 300 millimeters. And I do not like 250 very much because you have to, when you are placing the reinforcement and then doing the concreting, you might find the space is little congested. So if I can go for 300 millimeter width, I would prefer that. And then you can look at this side. What is the span? 7.5 meters. And you can see more load is coming. Trapezoidal load. More load is coming. And then there's another concentrated load. So what do you like? 300 or 400? I prefer 350 or 400. Why? The reason is this beam is having a greater span, it carries more load. High load means more shear. If you're having more shear, what do you like? A very small cross section or reasonably large cross section. We like a reasonably large cross section. So although we select 300 millimeter for this beam on grid A, for the beam on grid 1, I might select 350 or 400. 350 or 400. So when I say these rules, these are the kind of thinking you can use for medium rise and high rise buildings as well. Because when it comes to slab, the slab in a 2-story house and slab in a 50-story building, will there be any difference? No, same slab. But the risk is much higher in the tall building. So because of that, we have to have a logical reasoning for selecting each and every parameter. We need a logical reasoning to select each and every parameter. Is that clear? Any questions?
There's one question in the chat box.
Yeah, what is the question?
Can't we consider long secondary beams as continuous beam? There's one question.
Yeah. So we are considering the primary beams as continuous beams. Secondary beams we detail as simply supported, whatever the condition, because there will be a deflection at the middle of a beam, though it's continuous. It is continuous, but the primary beam is going to deflect at the center. So if the primary beam is deflecting, can you design it as a continuous beam? The answer is no. You should not design it as a continuous beam. You must design it as a simply supported beam. Even if it is continuous, still we design it as a simply supported beam. Is that clear? Is that clear? Engineer Manjula?
Yes, another question, sir. The depth.
What is the question?
About the depth.
You better read the question.
What about the depth of the secondary beams? How it is selected?
Depth of the secondary. Good question. Because now we know we are having 600 millimeter depth. So if we use 600 millimeter for secondary beam, what will happen? We have to crank the reinforcement because bottom reinforcement is clashing. So what is the preferred depth for secondary beam? 500 or 550. Never use 600. Never ever use 600 because you will have a lot of extra work at the site. The moment you select 500 or 550, automatically the reinforcement will go one layer above, and that will not create any clashes, no cranking, very easy to fix the reinforcement. The depth of the secondary beam is 500 or 550. How about the width? You might use a width like 250. You might use a width like 250 because 200 is a little difficult to fill the concrete. Not that easy. You have to order little flowing concrete. So better to go with 250 as the width of the secondary. Have I answered the question?
I have a question to addition, same
Yeah.
question. Can we use hidden beam for secondary instead of providing a larger depth? Can we increase the width and use that beam as a hidden beam?
Yeah, actually, why do you want to hide it? Because when you use this type of arrangement, it might be cheaper to have unless whether you try to hide or not, secondary beam can be seen. So if you don't like beam seen, have a seat. Because anyway, all these buildings, 2.7 meter, we'll have a seat. So why do you want to hide anything? Anything above the ceiling, no need to hide. So because we are having beam system, we are having services, we need to have a ceiling. The ceiling will be at 2.7 meters. So we are not going to gain anything by doing, you selecting something shallow as the second. Select something as deep as possible, but whether it's 500 or 550, that's your choice. You will draw the reinforcement arrangement, cover all these parameters and decide. Generally 550 works, but if you want, you can use 500. Have I answered the question? No winding going for shallow ones because shallow beams are inefficient. Shallow beams are inefficient. The whole idea of second beam is to have an efficient arrangement so that we can minimize the reinforcement in the second beam. In doing so, we can minimize the total reinforcement quantity for this particular site. Any other question?
Excuse me, sir.
Yeah.
Sir, when two secondary beam intersecting at the point, will that those two are in same depth or any stiffness
Yeah,
ratio
you
should be
can
made?
use for in 7.5 meter direction, you can use 550. In the 6 meter direction, you can use 500. That way you can make sure no clash. So in the 6 meter direction, 500, 7.5 meter direction, 550. So that way you can ensure, because you are covering all this by using a ceiling. So whatever you do above that, no matter. So you can ensure reinforcement can be fixed without cracking. And that is very valuable.
So excuse me, sir. May I ask a
Yeah.
question?
Yeah.
So some architects, they request put a slab or hidden beam into the slab. Then
That is for houses. That are not for.
yes, houses. Then can we design that hidden or slab beams as a beam, conventional beam, or are the beams taking actual beam actions?
No, you have to use, there's a method called Hillsborough strip method. So when they ask for slab beams, you have to use Hillsborough strip method and design the reinforcement, and you can learn about Hillsborough strip method by using the book by McKinley. Not by
McKinley book, right?
McKinley has it, and also Muslim Banji book.
Muslim Bangi, okay.
Has that method. So it's a method of selecting a particular width for the beam, and then concentrating a lot of reinforcement within the beam, so that beam itself the slab itself can carry higher moment. It's for strip method. You can design slabs by using that method.
Okay.
Right, so just read. You can even on the web. Sometimes you can download these books. So find a hard copy or a soft copy. Just go through the Hillsborough strip method and book by Mosley and Banchi has covers that sufficiently well. And I think McGinley's book also has the same kind of coverage. Okay?
Okay, sir.
But architects don't ask this kind of special request in buildings. All these come in houses. So if it is the case in house, you can use another method. What is that method? Use a 100 millimeter beam, steel beam, hidden inside the slab. Will it work? Yeah, it will work well. You have a 150 millimeter slab and you put a 100 millimeter, one or two beams inside the slab, and the beams are designed to carry the load. Composite action.
So then how to provide the reinforcement?
Reinforcement, because you have a 150 slab and you are having only 100 millimeter, what do you call, 100 millimeter beam. So you can run 8 millimeter bars above it, so that you get 15 millimeter cover. And 15 millimeter cover at a special location, if you are using 30 megapascal concrete, will be sufficient. If you are using 30 megapascal, if you are using 25, may not be sufficient. Or otherwise, you select the slab thickness of 160. Select the slab thickness of 160, then you will find that the cover is sufficient. Cover is sufficient because we are talking about a house, 30 megapascal concrete, very mild exposure conditions. So the house gets to last only about 100 years, because after about 100 years, there will be enough people who want to do something else. So generally we like something like 100-year lifespan, and that can be obtained by using 30 megapascal.
Sir, excuse me.
Yeah.
If we just use one secondary beam in this particular example, which divides 6 meter span into 2, and is it work? We can design them
Yeah,
as
if you
one
want, you
way.
can do that, but then the problem is the slabs will become one way. The reinforcement spacing should be reduced to 200 centimeters. Then the one-way span is absolutely to T10 at 200. So you can see you need more reinforcement. So two-way is very efficient. So I prefer going with two-way rather than one-way. But dividing only in one direction is possible. It's very much possible. In that case, you might say, I'm going to divide it like this, and instead of all these slabs, what I'm going to do? I'm going to have nerd beams, nerd system, where you get beams like this, supported at 1.45 meter interval with a thin slab of 60 millimeter. You might do that. And these days it's a very efficient system. Why? 3 meter, so you can have, instead of using the minimum depth of the beam, you might use a slightly greater width, greater depth for the nerd beam. What will happen? It will be very stiff, and the resulting system can be very efficient, very efficient. So one of the options that is available in the present context, where the reinforcement is very expensive, the concrete is also becoming expensive because of shortage of cement. And sand is already very expensive. Going with nerd system as a one-way slab system can be very efficient and cost effective. And you might be able to reduce the overall cost of the project by 30% by adopting these slabs over and over again.
So, excuse me, sir.
Yeah.
So, if for example, for the balconies, the slab is cantilever by say 4 feet.
Yeah.
Now we are providing two beams at the two corners, two edges. Then can we design that slab as a simply supported slab which is supported on the two beams? That we are providing the bottom reinforcement perpendicular to the two beams. Is it okay?
So basically what you are saying is slab will look like this. You are continuing the beam, you are putting an edge beam. Yeah, I mean,
no, sir, we are not. No, so we are not providing the beams along the longitudinal direction, only the shortest direction.
That is not a very good arrangement, because although you provided the middle part of the slab will behave like as a cantilever. This part of the slab will behave as a cantilever. So if you are doing that, put a small beam on the edge. Put a small beam on the edge. Then it will be safe. Otherwise, you have to design it as a cantilever. Not as a simple support. It's wrong to design it as simple support, because it's very unlikely that it will behave as a simply supported span in this way. No, very unlikely. It will always, its center part will try to behave as a cantilever. So don't do that. If you are going to rely on these beams, put an additional beam along the edge so that you will have a stiff, very strong cantilever. Very strong. Basically, it's not a cantilever, it's a cantilever with beams. Slab is just sitting on the beams. Even if you don't try to reinforce this slab will sit on it because there will be arching action. So they will not be able to, so you can provide the nominal reinforcement in the slab. Any other question?
So when we model a building, the ETABS or sub 2000.
Yeah.
Now, for example, moment is coming around for the columns 10 or 5.
Yeah.
But the code says that we have to take the minimum moment of axial load into 0.02 times.
Yes,
I think.
that's right.
Then what is the correct answer that we should take the code. When we take the values from the code, sometimes probably higher than the ETAPS movement.
Yeah. Take it from the code. Like you have to use the minimum.
Minimum. Okay.
Minimum extensity. The minimum extensity for the load should be used.
Yes.
Right. So now you are convinced how to handle the slab and the beam. And for every reason you have a logical reason. Not just looking at another structure, you are assuming we have reason to select the width, we have reason to select the depth. Then what is left? Column. So what is the size of the column? $350 by $350, 400 by 400, 450 by 450, 500 by 500, 600 by 600. What is size of the column? Any guess? 5-story building. What is size of the column? How do you find size of the column? We forget about all these lifts and all that. We say we find the load on this area. We find the load on the tributary area, center to center. Whatever the way we use it, all these loads will finally come onto this column. And we say self weight, we can calculate. We can calculate the finishes, partitions, imposed load reduction. All parameters are known. Then it's a matter, it's very easy. You know the load on the column. Sometimes you might increase it by about 10% to allow for all these pattern loading and all kind of things. Now you know the maximum load of the column. So these days we have to move to Euro codes, but I'm sure most of you are familiar with British codes. British codes are very simple but restricted. Euro codes are more complicated, but you can do many things, very flexible. So because of that reason, I prefer Euro codes. I used British codes a lot, but these days I prefer Euro codes. Why? Euro codes are really good. You can stretch things to the limit. Why do you have to stretch things to the limit? You don't have resources. Resources are very expensive. So I must minimize the use of resources. How do you minimize the use of resources? And that is by using good quality materials, which are stronger. And for that purpose, Euro codes are better. But when you are trying to find the size of the column, you don't have to worry too much. You can find it by using the British code simple rules. There are equations in the British code which says if it is a column n is equal to 0.45 FCU AC plus 0.87 FY AC. This is the steel area, this is the concrete area. There's an equation like that given in the code. Then there's another equation, n is equal to 0.4 FCU AC plus 0.75 FY AC. Then there's another equation, n is equal to 0.35 FCU AC plus 0.67 FY AC. There are rules, the equations. And if the column is subjected to some moments, what is the equation recommended in BS 8110? The last equation. The last equation is the one that is recommended in BS 8110. Now let's see. We know the load. You can calculate the load. Then you can calculate the column. And the most likely case is the column size will be one of these. Column size will be 400 by 400 or 450 by 450. Very unlikely that you need anything bigger than that for a 5-story. For a 5-story building, 400 by 400 column would be quite sufficient. But now we remove the shear walls, no concrete walls, only few columns around the lift core. Who is carrying all the lateral loads? The frame is carrying all the lateral loads. If the frame is carrying all the lateral loads, what will happen to the frame? It will go into behavior like this, or it can go into a behavior like this. So what is the most likely deformation of the frame? First one, A or B. The most likely deformation of the column is B, because there can be relative movement between the bottom of the column and top of the column due to the windows. So because of that, we have to consider this unbraced and unbraced column. What is the effective height? Can be about 1.2 times clear height. Now the clear height is 3.6. 3.6 into 1.2. Can somebody give the answer? 3.6 into 1.2. But you can see it's not 3.6. The clear height is 3 meters. 3 meters into 1.2. 3.6 meters. 3.6 meters. 3.6 meters. And divided by 500. Answer is about 7.2. And we know it's if you want to design it as a short column, the ratio should be less than 10. The ratio should be less than 10. Effective height divided by the minimum dimension, the applicable dimension should be less than 10. Now you can see if you select 500 by 500, you can satisfy that. But if I am designing this 5-story building, the size of the column I select will be one of these. You will ask why. I will not select 400 by 400 or 450 by 450. I select 500 by 500 or 600 by 600. And you might say it's a waste of material. I would say it's not. Because if you consider the material usage, the most of the material goes into the slab. A significant quantity of material will go into the beams, and columns will consume the least amount of material. So if you increase the size of the columns slightly, it's not going to give you a big penalty, it's give you a small penalty. But there's a big advantage of going for 600 by 600 column. What is the advantage? If there's an earthquake, I'll take a small frame where the hinges can occur. Hinges can occur at all these places. But we know always hinges will occur in the weaker element. And we like the hinges forming in the beam, not in the column. So if I want to make sure hinges form in the column, I must make sure column is bigger than the beam. And because of that reason, I would say I prefer 600 by 600. 600 by 600 column. And the building will look very strong, but after the earthquake, it will be one of the structures that are standing tall. Whereas your optimized structures might not be there. And what have you optimized? Column, which is consuming the least amount of reinforcement. You have optimized the column. And that structure may not be there. So, can you see the logic, Manjula?
Yes, we can.
Because we should not think about the code. Code allows us all these equations. We can do calculations, but we must look at the big picture. We must look at the big picture. So when you look at the big picture, we do not like hinges forming in the column. We like hinges forming in the beam. So make sure column is bigger than the beam. And I might use the same column size over the full height because changing the size of the formwork also will be costly. Then how do you provide reinforcement in the column? How do you provide reinforcement in the column? We will not provide 6 bars, we will provide something like 12 millimeter reinforcement, but we will provide 9 bars. Then we will go for a link like this, and we will go for another link like this. And what is the size of the link? T8. Never use R or minus T in the column links, because minus T cannot provide sufficient confinement in case of an earthquake. Then you have to ask the question, can earthquakes hit Sri Lanka? Unfortunately, answer is yes. Answer is yes, but not very high magnitude, but magnitudes up to about 6 on Richter scale is a possibility. Because these structures are designed to last 100 years or more than that, no point in taking a risk saying no earthquake will hit this structure. Let's take some precaution. Precaution is we select it in such a way that it's not going to collapse in an earthquake. Can you understand the reinforcement arrangement? I'm not selecting very large vertical reinforcement, but I'm more concerned about the confinement. So because of that reason, at the top of the column, I might select T8 at 100. Middle part, not a big problem. I might select T8 at 150. Okay, bottom, T8 at 100. And someone might say T8 at 75. If you want, you can have it. But having too much reinforcement is sometimes it's a nuisance when you try to do concrete. So I prefer some gap like 100 millimeters, so no honeycombs will ever come. Compaction can be done very well. Because we are using T8, we are taking a precaution. So because all these rules are based on laboratory experiments. Very few are based on real size buildings. But you can see every 100 millimeter we have 2 links. So that is providing significant confinement to concrete. And we are expecting very low magnitude earthquakes, like earthquakes of magnitude less than 6. So because of that reason, you can say this kind of detail would be sufficient. And if you want to be more conservative, you might select T8 at 7. T8 at 7. But Again, you have to see, when you are going with Eurocode, T is replaced by H. We call it hot roll bars, or QT bars, or Q quenched, QT bars, or QST bars. So the industry, it is either called QST bars or QT bars. Quenched, self-tempered. Quenched, self-tempered is QST. The short form is QT bars. Quenched and tempered bars. Quenched and tempered bars. The way that the reinforcement works is, when the reinforcement is very cool, very warm, we spray water onto it so that it will melt, it will solidify suddenly, while the middle is still red hot, and then it will relieve some of the stressors, and we get a reinforcement that is strong on the skin, soft in the middle, strong in the skin. Because it's strong in the skin, you can bend it easily, rebend it. Nothing will happen because middle is very soft. Middle is like mild steel, out is like high tensile steel. So the flexibility of the reinforcement is very high. When you do a bend test, there's very little chance it will fail. You always pass. Why? It's a flexible reinforcement. And that is the modern manufacturing method for reinforcement. So I have told you about reinforcement, why we should use T or H bars rather than mild steel. Mild steel cannot provide lateral confinement, so if you want an earthquake resistant structure, never use mild steel, use toe steel or high strength steel or hot roll bars for links. Is that all clear? Is that all clear?
Excuse me, I want to know how
Yes, go ahead.
Yes, it's clear. Very clear.
know how to
You want to know how to?
width of a beam. Width of a beam,
Depth.
not depth. Width of a beam.
Width of the beam, I explain you. Width of the beam will depend. The minimum width is for main beams, I prefer a minimum width of 300 millimeters. I'm going to get a lot of reinforcement, so I can easily fix the reinforcement. Whereas for secondary beams, I'm okay with 250 millimeters. 250. And then I told you, if I'm having H beams which are supporting secondary beams, I would again prefer a thickness like 300, 350 than 200. 200 might do the job, carrying the load, but it's a weak beam. So I like a stronger beam. That's H beam. Have I answered your question?
Okay, thank you.
Sir, excuse me, sir.
Yeah.
So for the medium rise building, for example, 2, 3, 4 stories, if it is not in a earthquake zone,
Yeah.
right? Then for the commercial building, can't we use the R6 for the columns according to the code? We calculate that one.
Because no way in the world you can say it's earthquake free. Every zone, every plate can have faults. So because of that, no way in the world you can give a guarantee no earthquakes. So because of that reason, make sure you use T8. And this use of T8 will encourage manufacturers to manufacture T8 so that it will be available, readily available in the market. T8 is a very, very economical reinforcement because you get 400 bars, minimum 400 bars per ton. So whereas you get only about 280 bars per ton for 10 and 180 bars per ton for 12 millimeter. So don't think D8 is an expensive reinforcement. It's not. D8 is a very good reinforcement that can be used, easily used for many applications. T10 is too much. T10 is too much. For small buildings, T10 is too much, but for large buildings, we use it. Now I have got the slabs and all. And how about the roof slab? You are continuing the same system, but the slab thickness you will increase to 150 millimeters. Why? In the roof slab, we will provide some additional nominal reinforcement within the slab top to ensure that the crack pitch will remain as low as possible so that the roof slab will not leak. So have I answered? Is it clear? We need 2 mats of reinforcement and the additional reinforcement can be out of T8. Additional top layer of reinforcement can be out of T8. Any questions?
So I have one question.
Yeah.
Sir, for the QST bars, if we make the threads for the couplers, will it have affected the strong area of the bar? Is it affected the?
Yeah, it can affect the strong area to a little extent. But you are using couplers to couple compression bars, aren't you? You are using coupler, not it's a coupler is a tension coupler or a compression coupler?
Tension coupler, sir.
Why do you need a tension coupler in a column? In the column, all the couplers will be compression couplers. So the reduction in area will not affect very much because the coupler will have additional area. Now you have to answer this question.
I have another question.
Yeah.
Yeah, it's related to the beam detailing. Let's say if you are using a 300 mm width of a beam, what is the recommended minimum width of the transverse spacing of the longitudinal bar? Let's say if it is 300 width, can we provide?
The minimum rule is 25. The aggregate size, maximum aggregate size was 5 millimeters. But I prefer something like 40 millimeter minimum. What is the reason? Then I can use a 25 millimeter vibrator and send the vibrator through between the bars. I can send a vibrator.
Yeah, that's okay. But I am asking the maximum spacing. Sorry, maximum spacing. Can we stick to 2 bars, or do we need to provide? Do we need to keep the rebar within less than 150?
If you look at the maximum distance rules, even in Eurocode, they are very comprehensive. So because of that, I always prefer using 3 bars of smaller diameter than using 2 bars of large diameter.
Okay.
Thank
you.
The closer the reinforcement, you will not get any crack problems. But if you try to minimize the number of reinforcement by using large diameter bars, you are generally asking for problems. So my rule is more small diameter bars satisfying the area. Now can I ask you a question? Which equation you will use to calculate the size of the minimum size of the column needed? Equation 1, 2, or 3. All 3 equations are given in BS. Equation 1, 2, or 3. We use equation number 2. Why? In a multi-story building, the axial load dominates, Bending moments are very small. Because of that reason, use of equation number 2 can give a better answer than the use of equation number 3. So we can always use equation number 2 because the moment transferred by the beams is very small. The moment transferred by the beam is very small. Because of that reason, we can always go with second equation. Is that clear? Manjula?
Yes.
Any other question you have? Because I'm going to touch on foundations. Touch on foundations.
Sir, can I ask a question?
Yeah.
So can we use T type, L, T or cross type columns in lieu of
Yes, of
rectangular
course.
column?
Of course. You know, if I do not like designing this as unbraced structure, and if the architect allows, I'll go for a column like that. What is the purpose of that column? That column is the wall in this direction. Can the building move? Can the building move? The movement of the building can be restricted by the column. So, can this type of column fail? No way. Why? It is restrained. One wing is restraining the other wing, or one leg is restraining the other leg. So, it will not buckle or fail because it is L-shaped. And using this L-shaped at 4 corners, will I get a braced building or an unbraced building? I'll get a braced building. If I'm having a braced building, then you don't have to worry even about earthquakes. You don't have to worry about earthquakes. Why? Because all the earthquake loads will now be taken by the walls, not by the corners. So the structure will not, very little chance for structure to suffer any damage because however the earthquake tries, the building does not move very much. Is that clear?
Yeah.
That's another option. Rather than going with the braced building, unbraced building, you can go with a braced building, provided the architect allow you to have some walls on the outer building. Is that clear? Now
Yes,
the foundation.
Sizes of these edge columns are decided.
So these edge columns,
Yes.
these ones, Manju,
Yes. Yes.
you can design it as a wall. If the length of the wall is length is more than 4 times the width, it's a wall. You are designed as a wall. Later I will show you how to design a wall. Okay? Next week I will show you how to design a wall if time permits. I'm just trying to give you an overview how to deal with different situations by having some idea about the big picture. Some idea about the big picture. I'm not interested in all the numbers in codes and all the equations in the codes because I like to see how the structure is going to behave. It really is subject to vertical loads and lateral loads. I'm looking at the big picture. I'm not interested in individual elements.
Excuse me, sir.
Yeah.
Sir, what could be the sizes of that edge column, sir? That L-shaped column?
L-shaped one, I would select a width of 225. Very easy to cast. 200 is also possible, 225. This way, I might say 1.2 meter. 1 meter or 1.2 meter. Your 1 meter is enough. And then you design it as a wall, not as a column. And 1 meter column, 1.2 meter wall is sufficient to give stability to the structure. And structure will become very strong. very strong. No, you need not worry about earthquake because it's a strong structure. But you have to make sure foundation is also strong. It's a 5-story building. I will not go with individual footings. I might put an inverted T-type foundation. I might put an inverted T-type foundation. And the advantage of inverted T-type foundation is differential settlements will not have any effect because differential settlements are all well looked after. And what is the shape of the inverted T? And the depth will depend on the type of loading and the soil condition. If soil conditions are weaker, we go for a greater depth because we might have to balance the situation by having a stiff beam. Whereas if you are having good sandy soils or laterite soils, you might consider a reasonable depth, not a very high. So the depth of the inverted T can be about 1 meter or 800 millimeter or whatever. But inverted T's are very efficient structures because even when you have a width of 2 meters, the thickness here can be 300 millimeters. No need to have anything more than 300 millimeters. Even when the width of the base is 2 meters, width of the base is 2 meters, width of the base is wide 2 meters, still 300 millimeter would be sufficient to prevent the shear failure while providing adequate flexion. And the reinforcement can be T10 at 200 or 150 or T12 at 200, something like that. Very small quantity of reinforcement. Very efficient system. How about the robustness of the building? Very robust, not like individual platforms. You can take external shocks very well. And then you might consider connecting these, if you want, with a ground beam, so that the foundations are connected in every direction. Very strong foundation. And then you might consider having a ground set also if the soil conditions are weak, supported on the foundation rather than so that the moment you have a ground slab supported on the foundation, the structure will become very stiff at that level, which is very useful if you are constructing on weak soil conditions. The time is 8:25. Shall I stop here because I have covered all different aspects of the building? Very low. It's a big building, 5-story building. But I have covered many aspects that you might often overlook. And you might always try to optimize with columns, but I never optimize columns. I always optimize steps. Because anything you say in the slab is repeated 5 times. So there's no point in, and slab consumes the maximum amount. So I might consider things like NERD's beam system, beam slab system, pre-const, and in situ const. In preference to reinforced concrete systems without secondary beams, or with secondary beams, or it can go even further. And you might consider pre-stressed concrete slabs. No beams at all. In a later day, I will show you how to design reinforced concrete slabs, at least how to think about design. And then, because if you go with PT, there are many advantages. And we are lucky because the company ranked the best in Singapore. Not one of the best in Singapore. Or the biggest in Singapore is very active in Sri Lanka. And that is called Utah. Very active in Sri Lanka. So you can easily go with PT, even in small buildings. Okay. Manjula, Shall we wind up the lecture?
Yes.
So excuse
We
me.
can wind up if any questions to.
Yes, but I can take 1 or 2 questions more.
So
Little more
excuse
time.
me.
Yes.
If we are modeling this structure,
Yeah.
if we are putting the continuous type of pad footing,
Yes.
what is the restraint condition that we can put for the columns?
You can say consider it as fixed.
For both direction, no?
If you have a ground beam, both directions.
Okay, sir. Thank you.
Excuse me, sir.
But you will have a slightly deep ground beam like 800 millimeter, not very shallow one.
Yeah. Even we can model, if we model it as a pin support, pin restraint one, pin support.
Yeah, if you want, you can do that, no problem. But really, in the real situation, it's fixed. The foundation is so strong, it doesn't rotate. So what is the support condition? Pin or fixed?
It should be fixed.
Fixed.
Excuse me, sir.
Yeah.
While designing the beams from the results obtained from E-Tapes or SAP 2000, we can't incorporate the pattern loading there. No? What is the best way to optimize?
I will not design beams. When I make a 3D model, I will never design beams by using E-Tapes results. I always go with. I just do a simple subframe analysis as given in the codes, and then do moment redistribution, and then design the beam for the moments that I like. But I do a trick, and that is called risk assessment. I know at the support, the moment can not exceed whatever I calculate from the model, but there can be redistribution of moments that can increase the moment at the span. So when I am designing the span moments, I might design for slightly higher moment, so that I will end up with little more reinforcement or extra reinforcement in the middle part of the beam. In the middle part of the beam, extra reinforcement will be there. So I will not use E-Tapes model. I'll just do a simple subframe on SAP 2000. And then apply the loads, pattern loading, and get the bending moments. They are all approximate, because if there's any settlement, all these moments can change. But fortunately, we are using inverted T-type foundation, no chance for varying the very little chance of variation of moments. So if the moments do not vary, you can easily select the middle span moment and then increase it slightly to allow for what we call risk analysis. The risk analysis is we like to have slightly higher factor of safety in the span section of the beam. Is that clear? I will try to have a slightly higher factor of safety in the span, because if the beam fails, it will fail in the span, not at the support. Is that clear? So basically, I will over design the beam at the center.
Excuse me, sir.
Few reinforcement extra.
Sir, can I have a question, sir?
Yes, we'll wind up now almost on time. We have enough time with future presentations. May I invite our presentation committee chair, subcommittee chair, Engineer Kamala Gunawardene, to propose vote of thanks.
Thank you, Manjula. Good evening, everyone. Sorry, I'm coordinator of this knowledge sharing, and actually it's a great honor for me to do this vote of thanks. Today we have completed the second lecture of medium rise buildings, the head in structural design methodology. A big thank to your professor. Thank you so much. Professor Dishan Jaisinger, thank you. for your
Yeah,
most
thank you.
worthy
Thank you
session
for listening.
delivered
And I
today.
hope you have gained something, a new way of thinking about structures rather than just thinking based on some rules.
Also, I thank the organizing subcommittees, professional and presentation and knowledge sharing of Civil Engineering Sectional Committee for this session. I extend also my thanks to the IESL for hosting this and IT teams for your supports. Finally, I thank you all our members who participated in this, and I hope you extracted essence of this valuable lecture series. Lecture this evening. Designs and construction of medium high-rise building will be a series of lectures, and you need to participants, you need to register for each session through MIS. So next presentation will be on coming Tuesday, 8th December, and we will notify the time after rechecking the other main events scheduled at IESL. Thank you, Professor, and thank you, everyone. Have a good day.
Thank
Good
you.
evening.
Thank you.
Thank you very much.